Welcome back to building an emulator in Python. I want to show you a couple of things. First thing that I want to show you is the state of the emulator at this point, which is as follows. So you notice I'll use a debug tag. Need to make this a little bit bigger. And you'll see the instruction shoot by. And for you this might be a little bit hard to see, but if I stop it, you can actually see it's looping between these three instructions and it jumps back. So what we actually reached here at this point is I think the start of the scrolling Nintendo logo, and in this loop the system will wait for some interrupt routine from the video chip to start what's called a vertical blank, and then it will start doing something. So at this point the program will run indefinitely unless I stop it. And something else is that you see here I've added a screen with a circle on it, and this is basically the start of our graphics. And here I will show you what I did. So I use a graphics module. I'll show you in a minute. You need to import that, and then with the init screen, and then very simple, I will have a name, a size, and it will not automatically update all of the screen all the time. And then I just draw a circle, but that is not really relevant, just to show you that it works. But I can hopefully use this system to do all the graphical stuff. I actually searched quite a while for a good graphical system. It was not very easy to find. So that my chat. So yeah, that's it, what we'll be using. And here's the debug statement. So if this is added, then it will be very simple. And then if debug, it will print. And so this is a little bit more useful when I want to run an actual program and see how fast it is or something like that, because these print statements are very slow. Okay, let me show you the graphics. So this is something I found on the internet. It's usable under GPL, and it uses Take-Inter, which is a very broadly available package. On Ubuntu I just needed to install one package, and I think on Windows it's installed by default. So this should work relatively well on all systems, but that's not really my main concern. And then here we have the simple steps that I showed you. I implemented. And what we'll be actually using mostly is we'll use image, and then that will basically, I think it will be something like a bitmap, and then we can change that bitmap, or we can have multiple layers of images, and then every so often it will be actually shown on the screen. I think 60 frames per second it will be shown on screen, so it won't be updated if it's not needed. Or actually it will go as fast as it needs to go. As fast as the emulator is. So yeah, this is what we'll be using. And this is where I got it from, this address. And yeah, I hope this will do. I think this is a good library, so I hope this will work. Okay, so I'm not completely sure what we need to do. Here we see our program running on forever. And we need to find out, but basically a bit of reading needs to be done on what we need to do to make everything work. So I've read a whole lot about video, about sprites, and well, not that much about the RAM bug. But I think for now we're going to focus a little bit on the interrupts. So that is page 32. So a little bit of reading needs to be done. So there are a bunch of special registers that we need to take care of. This is an interesting one. Which will show you what kind of interrupt has been done. And then we can start doing something with it. So yeah, let's have a look at our, I'll stop this. Let's have a look at our memory. So apparently, if something is written to that register, then something needs to happen. So if address is ff0f, and interrupt something. I'll say byte written to interrupt flag. And for now, I'll do the same thing when we read. Let me just check what this system will do, what these instructions are doing. So here we have those instructions. Here it will load ff plus 44 into A, and then compare A with 90. So basically, if it's a vertical blank period, then will not jump, and if it's so a little bit more detail. So it will get the value from this address, put it in A, compare it with 90, and if it's equal to 90, then it will be 0. So since it's a jump if not 0, it will not jump and it will continue here. But if it's not the case, then it will be not 0 and it will jump back to 64 and continue the loop. I think this is a signed integer, so unsigned to signed integer. And oh sweet. Unsigned character 44 is 64. Oh wait, this is all going wrong. Next to decimal. What value did we have here? $44, so that's decimal 44. So what I'm trying to figure out is where why it jumps to FF44. That doesn't really make sense to me. Let's just finish this off. Byte read from because what do we have at FF44? That's maybe the question. We have all kinds of stuff, sound stuff. Yeah, I figured it out. So it will read this register, LY, and that will have a V blank period between 144 and 153. However, it will so it will start at 144 and end at 153, but in hex that's actually 90. So what we have here, this one, here we have 64. It compares with 0x90. Yeah. So what we need to implement is actually that our graphical system increases that ly value every so often. So that's very interesting. Okay, well, we'll put this in here. If address is FF44, this is ly, byte read from ly. And then we need to implement our graphical system also. So it doesn't say that it's reading from that byte. So let's have a closer look at our instructions. We have FE 20 and F0 at 66. Zero, 1, 2, 3, 4, 5, 6. So it's FE 90. Sorry, it started at 64. 0, 1, 2, 3, 4. F0 44. And then I want to know what is it instruction doing. So I'm looking for F0. LDHAN. We can see here, we will read, but I want to see the actual value it's going to access. So I'm going to print this out. Print address like that, and then here let's do 6. Yep. So now we can see it's doing something. And it's actually reading 0044 and not FF44. That's not good. And I'll think I need to do oh yeah, I see it. Plus was good, but this needs to be, because we are dealing with a with an address, and addresses are 2 bytes and not 1 byte. Normally I use that to mask a double byte, a single byte. This time it was a double byte. Yeah, so it's accessing address FF44. Memory, but oh, this is read word. Yep. Read byte. Yeah. Now we can actually see that we are reading the LY. But we need a graphical system. So we need a GPU. Python. And I don't know what our GPU will do yet. But for now we'll have it like this. So now from GPU import GPU, and then what I think we'll do is to create the memory. You need to pass the GPU in it, and later you will also need to pass the sound in, and maybe the input handling in. So GPU will be passed into the memory. And the memory passed into the CPU. So the GPU is a subsystem of the memory. And we'll do it like this. GPU is GPU. And what will pass into the GPU is this window handler. That screen init thing. Yeah. Or maybe even we'll move this to the other file. And we'll move that code to the GPU init. Let's still put in there. Yeah, that memory will have a GPU. So then we go to GPU. Import the graphics. We need to move this function there. Wait, I need to copy this. Hello, Johnny Bravo. So, like this. This can be removed. And this can be removed. And before I forget, yeah, this is an important value, win. Because that will, you need that to write pixels to and stuff. So we go to the memory, and we get our GPU passed into this. I'm not completely sure why we need this, but maybe in time. Oh, you can call methods on it. So you can say self.gpu is GPU. Self.win is that. So then you can, from the memory, you can do certain things. So for instance, you could say, here you could say, if ff44, then return GPU self.gpu dot get ly. Yeah, something like this. And then we'll implement a method get ly. Defines here. And then we return well, 0 for now. We'll print GPU ly. called something like this. Let's see if it still works. Where old syntax. Name error win is not defined. Oh. Oh yeah. So here, self.win. And we're back. And as you can see, it doesn't actually show it doesn't actually show us the circle that we should see, and that's something we can fix. So here, within our loop, we can count cycles, and maybe need to do some calculations. So every cycle that we count here is a 4 megahertz tick. And to be a little bit more precise, editor and get our reference. This is our frame rate, and this is our clock rate. So many hertz, or 1 over 414,304. So every this is a second in if you see these cycles, but we don't want whole seconds. We want well 60 seconds. So I need to divide this through what does it say? 59.73. 9.73. And that probably gives us a whole number. 4194304 divide 59.73 is, well, this. And is that divisible by 4? I don't know. It is not. 0220 divisible by 4. This is. So we'll use, for starters, we'll use this as our like vertical cycle counter. And So we'll count vertical, count well, maybe we can do that in the GPU. We'll do it in the GPU. We'll move this, and we'll say C is cycles plus C, and then GPU dot tick C. And then we'll need to build a tick function in our GPU. With the number of cycles. So cycles plus is tick. If cycles is over or equal to this, that means a vertical sync frame needs to be done. Reset cycles. And we will draw self and win update, and we'll put in a print for now. So we can see it. I forgot. And it's not working. It doesn't seem to be drawing. GPU.tick. Okay. Am I actually increasing myself? Yes, self and cycles. It's over that. Make it a little bit more stand out. Yeah, this should work, in my opinion. Yeah, when this is over 70,000, it should redraw. Ah, it does work. Yeah, but that's good. That works. It's probably even it's probably not that slow even. However, it seems that our CPU is very slow, so we can run it without debug, and it's much faster. Yeah, and it works. Okay, great. So back to our no, we need to be in the GPU. So according to our documentation, indicates the vertical line to which the present data is transferred to the LCD driver. The LY can take any value between 0 and 153. So basically, the vertical resolution is 144. So that will represent the graphical driver is busy writing those frames to 144, and after that nothing, theoretically nothing is happening. So then you can write to the V memory between these two periods. But we will do it probably a little bit different, because we will not need to print data to the driver, but we need to set this value to be correct, because programs will use that to calculate how much time they have left in that frame. And that is why we need to do another calculation. So this is a full frame in terms of cycles. Right? Yeah, that's a full frame. So that divided by 720 cycles. That divided by 154 should give me should tell me when to update the LY. So let's do that. Where is my yes? So let's have a go with this. Divided by 154. Yeah, it doesn't divide very nicely. This also doesn't. Yeah, I think I'm just going to round this off. I don't like rounding. So if it ticks, I'll have these cycles. I'll call them V cycles. I need to set the LY to the appropriate number. So LY is the number of current V cycles divided by 154. No, not divided by. Divided by, what do I have here? 456. 456. So that will mean that at tick 70220, yeah, if I round this up, then it will have the last maybe I can do this even. So 70220 divided by 153, 459. So the last value, 70220. Yeah, this will, or if I just use the old one for 16, and then just floor it always. There's a floor function. So it's the last value, 154. This is 456. So once more, divided by and then floor this down, it will be 153, which is the maximum value that it will hold. And of course, if we divide it by 0 divided by 153, it will give us 0. And everything in between will be mapped to that. So if you just do floor this, but I don't know if that exists. So this should work. Import math. Let me just quickly check if this will even run. I need to add a function, close. That will close the window when it breaks. this is of course self.vcycles. And then now in the main, I need to, yeah. So I've made this exception if the whole thing breaks, then it will print the exception and raise E. So I can do some things on close, and also like print all the registers and stuff. It's very useful. Yeah, this seems to work, so that's good. But what we, get why it's called. What we of course need to do is we need to actually write it to memory. So we need to have access to the memory, right? Like mem write byte 0xFF44 and ly as a value, but I don't have access to the memory yet. That's annoying. I would give myself access. So here I create memory, I create CPU. Here I put GPU in memory. What if I do this? GPU is GPU. I say GPU dot set memory mem, and GPU and mem dot GPU. Well, I don't think I need that yet, so I'm not going to do it. Memory. Because I don't actually think I need it here yet, so I mean this is, you know, not strictly necessary, because memory will be memory, and it's better to have just one place where all this stuff is being handled. I might need it for some special functions like the control register. Yeah, but that will come. So, well, I want it in the constructor, because this will not work without memory. But it will work the other way around. Memory will work without without a GPU. And the same goes for sound and all that kind of stuff. So yeah. Let's see how this goes. CPU, man, GPU. That should work. Yeah. Okay, it's actually really nice. So you can see here how it keeps copying the 8B into the A register. So that was that function that we saw explained over here. So here it loads that the value at that address into A. It will compare and it will possibly jump to 6A. So if we look at here, 8C, 8D, 8E, 8F, 90. Here you can see jump back. It doesn't jump back to 6.4, but it goes to 6A. Then what happens then? It decrements C with some kind of value. That's not explained here. Decrement C. Oh, here we have C. So we start here with 0B, 0A, 09, 08, 07, 04, 03, 0, 0, 0, 0, 0. And then when it hits 0, it continues. Jump not 0 to well, it jumps back here all the time. It jumps back to 6.4. And what I think this will do, this is actually scrolling the thing. Let's see, deck E. But I think we are missing one instruction. Instruction 90. I think either this one, or oh, we're much further on. Here we load 13 into C. That's what we see here. We increment H. H is incremented here on 7.3. Then some sound stuff is happening. That's cool. Then we compare. Continue, 7E. And jumps to 8.6. here, and then I think we will end up here. Yeah, instruction 90 at 88. That's a subtract, and I don't think we have a subtract yet. So let's have a look. Yeah, subtract. So I think we need that. Subtract. Subtract n from b. Okay, so let's code this in. I also think we don't even have the add. So we do not have add, we don't have subtract, but that will change now. So it will be subtract n from a. So I'll interpret that as we subtract a by something, and we'll call this n. No, call this reg. Register b in this particular case. How many cycles? 4 only. That's pretty quick. Program counter 1. I'll put it around this place because here we also have increase and decrease, and it is very similar, of course, to subtract and increment. Add. Sub a register self. Well, what we'll do, I'll have this. And that will actually take a value, and this won't take a register, so this will just call self.sub a n with as an argument self.get register 8 with argument 0. And you can see I did the same thing for, I did something similar here. Oh no, that's not right. Here I used a similar structure, and I will also use this indirect thing because we need that as well. So what do we actually need to do? We need subtraction, and we need all this flag setting. And I think this is actually very, yeah. Actually, this actually is exactly the same as this one, but only this one doesn't even store the result. So I will just copy whatever is there. Push pop compare. And as you can see, it's a little bit complicated. And that's why I don't want to do it again. Like this. And we'll say val itself get a minus, is that correct? Sub n. Yeah, so this is a minus n. A minus n, and I will mask it off. And then of course set it, store it in a and all this stuff is flag setting, so just quickly run through it. If it's bigger, then we don't borrow out of A. So if A is bigger, then we won't borrow the carry byte. And that means we need to set the carry, so else we don't set it. If they're exactly the same, we know the result will be 0. So if they're the same, they will set the 0 flag, else we will clear it. And this is the half carry, which is very similar to this statement, as in, is the first part bigger than the second part, then we won't need the carry flag. So it's the same thing as we have over here, but then we have these masking statements, and what that will allow us to only look at the first 4 bits. And if this part of A is bigger than this part, then we know that this value will not be borrowed, and then we set it, and else we clear it. Then that's very cool. I like that. Yeah, I think we should be good to go with this. So what I then do, and what I did off camera a lot of times, I then add all the other opcodes that do the same thing. So, and since they're on a row, we can do it quite efficiently. So let me just quickly go through it. We were at 9.0. We need to go up to 9.7 and D6. So first up to 9.7. So 9, 2, 3, 4, 5, 6, 7. And this one is with A. And then we start from B. 96 is HL. Which I will call indirect HL. No need for this, but it will actually take 8 cycles. Then we have 9.5, and that will do for L. 9.4 will be for H. Yep. And then E. C491. So now we are almost ready, but we need this one actually. So we go back to our subtraction. What we need this one, and it will be relatively simple. Except for the fact that it needs to store. No, it's fine. It will store the result in A, so it's good. We're good. We'll call the function with an argument read byte, and that is self.get HL. So we get HL, we get the byte from at that location, and we put that into our subtraction. Not too hard, I think. Yeah, the result will be stored in A. Okay. And there's one thing that we need to do more. That is D6. That is the direct immediate command. So we go to 0xd. D6. Right? Yep. And we can use our AN for this, and then we can use our immediate 8 call for that. Immediate 8 is true. Cycles, how many cycles? Also 8. And program counter 2. Comma there. And then I think I made a mistake. Yeah, here this needs to be a string. Then we could quickly check if this will work. It should crash somewhere else, I think. Yeah, it crashes. Oh yeah, I already know what I did there. So when I use these functions, I of course need to push in the arguments as a list. And I think I do the same thing with this one. Well, I don't yet. But else we get this nice error, which is actually helpful. Yeah, it's doing good. We can see the H going up slowly, I think. H7. I don't know if you guys can see it, but this is now 7. 8. 9. So it's, I think this means it's scrolling the Nintendo logo down. And let's see until where it scrolls. Until B. It's decrementing B. And decrementing C. So we can see C is 0C. And B 0, 1. H is still going up. But I don't know when it will stop. And just for those who are interested, when this counter, the last counter, when that hits the value that I have here, when that counter hits this number, that means 1 second has been emulated. So with this debug mode on, it is really slow. So we're now not even close to 2 seconds emulated. But that's okay, because I never intended for this emulator to be very fast. But the point has been proven, and I think this will count until D hits 0, because this D register is slowly decrementing. So while that's running, let's have a look here. So here you'll see dec D, and there at 8C, it will jump if not 0 back to well, somewhere here probably, and then it will decrement B once, and we're currently at B number, well, that can then also be 0. It will jump to E0, or it can jump back to 060 and wait for a VSync, and yeah. So it's good fun. So more than 2 seconds have passed now, and when this C value drops to 0, something interesting should happen. Or in this D value. Just gonna run it a little bit more. Because it will be, something will happen probably. And then what we can do is we can update our little table that I have built. I've built a table which shows all the instructions that I have or have not made yet. And we did 9.0 up to 9.7. So we're going to add those in. And we did, what was that final one? D6. We also did D6. So yeah, and this will fill up nicely. For each time we do such an instruction, we'll usually do 8 at a time, so we only have a few more left. So this is, I think, add, this is another instruction, subtract, this is another subtract, and then it will be full before we know it. Yeah, so this time it actually did something. It did not drop the D exactly till 0. So at program counter 8.4. Oh, this is another vsync. Those take forever. What do we have here? Oh, that's not supposed to be at 8.4. We're supposed to be at either 8.3 or 8.5, but not at 8.4. 8.2, 8.1. Yeah, so maybe 8.1 has a wrong kind of program counter increment, or 8.2 moreover. So let's have a look at instruction 8.2. This is fine. Find 0x82. So which instruction? 0c. Yeah, there's a program counter increment of 2, but it doesn't make sense because it's probably just a register, increment a register. But we'll quickly check it. 0c is an increment, and yeah, it should only increment the program counter by 1. And I have another very useful table. This is this one, which also shows you that kind of information. So it says, yeah, size bytes 1. So it's just 1 byte. So this is wrong. And let me search quickly for other increments, because we might have that error in multiple places. So, inc. One program counter. They have all one program counter. Yeah. So yeah, that should be fixed. So what's annoying now is that it will be very slow if I don't do this. And also I'm going to remove those print statements. I'm just going to say pass. read and address. Yeah, so this is a little bit quicker to do it like this. And you see that we have another instruction that we don't have, and that's instruction at F4. So that's an add instruction, and we have never built an add instruction. I know that. I was actually quite surprised that we are almost through the entire bootloader, and still we did not manage to use any add instructions. So that's kind of funny, I think. And it says here it is 8.6. So let's build it. 8.6. Famous number in computer science. Let me look it up. So actually I'm not going to start with 8.6, I'm going to start with 8.0 because that's way easier. So it's very similar to the subtract, but then it's add. So let's start with that. Add 8 A and then reg, not 8. And you can see the subtract is actually there, so it's not only similar in how it's implemented, but it's also similar in opcode. Register B, and then we have another cycles for program counter 1. Let's build it. Under our subtracts. And just like before, we actually call this function. Get register and close it in a list, and then we build the actual thing above it, which will have a value in it. So for starters, I'm going to copy what we have for subtract and then paste it. You may actually notice that I'm copy and pasting code quite a lot, which is usually not very smart to do, and I'm not saying that it is very smart in this case, but I want this program to be very, very quick, or at least as quick as possible, given that we're using Python. And something that's actually quicker is just to copy paste the code and use like all this if else, if else, if else. That's very fast. If we use a lot of weird constructs, then it's probably gonna be slower. But if you do have a suggestion for how I can do it better, then that's also more than welcome. So now we're doing almost the same, but I'm just going to do this. But what can happen if this is large and this is also large? Then it will be a larger value than 256. And in that case, the carry flag needs to be set. And to check that, it's actually very simple. You just say if val is larger than 0xff, then it will set the carry. 0 is a little bit different. We'll just say if val equals 0. Half carry, that's interesting. So what I'll actually do is, it's very simple. Instead of using this larger than sign, I'll use plus. So if a and what we plus it with will result in a carry, that's the same as to compare it with is well, basically if that is larger than so if it's larger than 11111 4 ones, then this will be a 1 as well, and this will be something like this 1 0 1. So that means bit 3 has a carry out. So let me restore this. So if it's larger than this one, the two combined, only the rightmost parts, then we have a half carry. And else we don't. And the N flag, I think, is always reset. So N flag is false. And let me quickly check if the subtraction has the same thing. Well, N is set here. Okay, that's good. So N is reset. And finally, we need to set val, but we need to be careful because we want to not set a value that's actually higher than allowed. So we mask it with this nice value. And then we are good to go. One thing that I'm going to copy is the indirect HL. Add indirect HL, add A, so I'll rewrite that. For the rest it's all the same. So cool. We have that built. Now we can copy paste this a couple times. 0, 1, 2, 3, 4, 5, 6, 7. Yeah, at least until 7. So this one is A. And then we start from 6 is HL. So it has very similar structure to subtract. And indirect L. Don't need that. More cycles. Yep, more cycles. No more broken counter, that's good. Then we just count down. So 8.5 will be L. H4 will be H. 8.3 will be D. No, E. Forgot about E. E. 8.2 will be D, I think then. Yeah, 8.2 is D. And then 8.1 will be C and 8.T will be B. And then we need to add one more, that is C6. Let me just copy one. So let's go down to C6. And this will be sub A directly. So N, no register, 8 cycles, 2 program counters, and will be me D8, 8. Yep. Well, let's see if this worked. Oh, I messed something up. Yeah, forgot a comma. I just want to nothing here. Okay, we got an error again. I think I forgot something. It's in add A and HL. Which I forgot to do this, read from memory. And I probably also did it wrong here. Always read bytes from memory. Yeah, and now it's actually reasonably fast. As in more than 1 frame per second. Which is totally fine by me. And it could very well be that it's locking up. Because, very simple reason. Well, not that simple, but what it will actually do is it will compare the Nintendo logo in the boot ROM with the Nintendo logo of the cartridge, and if that doesn't if it's not exactly the same, then it will basically lock up. So it will I'm not exactly sure what it will jump to. Plus FE. I don't know what it will do. It will probably do something weird. And that's the downside, is how I cannot see what it's doing. Only until I interrupt it, then I will see. Nothing yet. So I will leave this part here. Thanks everyone for joining me today, and I'll read some more about the video, and then next time we will try to implement some more of the graphics to get that to work. Thank you for joining, and until next time.